everybody, Jeremy Blum here with Arduino tutorial number 10, sponsored by Element 14. This is the last consecutive video tutorial that I'll be doing. I hope to continue doing more of these in the future, but this is the last one that I'll be doing on a weekly basis. This week I'm going to be talking about interrupts on the Arduino. Now there's two types of interrupts that you can use, a timer interrupt and a hardware interrupt. Arduino has good libraries built in to handle hardware interrupts, however timer interrupts are quite a bit more difficult. I'm not going to focus on them in this video, but if you're interested in using timer interrupts for some reason, go visit my blog. I made a post a few months ago about timer interrupts, and I have a very long, detailed code example about how you use them, and it's well commented, so that should help you get you started with that. If you want to use hardware interrupts, you're in the right place, because that's where we're going to start today. Hardware interrupts are really great because they allow you to execute code on the Arduino while still looking for input from the outside world. So for example, you could be running some code that turns a motor or something, but still look for a button press that changes the speed of the motor or anything like that. Ordinarily, you'd have to accomplish this by polling the button state continuously in a loop. But if you're doing something in a loop that takes a while, like running a for loop, for example, then you might not be able to do that. Interrupt handles it by letting you feed something into a pin on the Arduino that's constantly polling it and checking it to see if it changes state. And then if it does, it'll execute a subroutine that you can specify. So let's start talking about the technical details of interrupts now. Let's talk about the different kinds of interrupts that the Arduino supports. There are 4 in total. The first kind is low. This means any time an input to the Arduino's interrupt pin is low, it'll keep executing that interrupt function over and over again. Usually we don't want to do this one. I've never used it personally. The next kind is called change. This means it'll execute a function any time the pin changes from high to low or from low to high. So if we have a pin input that looks like this, it'll change at these 3 points. The next kind is called rising. Rising executes a certain subroutine any time it detects that an interrupt pin goes from low to high. So it wouldn't execute here, but it would execute here and here. Falling is the exact opposite. Falling interrupts execute when an input goes from high to low, just like it does here and here, but it wouldn't execute here. These are the 2 that we'll use most commonly, especially when you're using a button input. Let's now talk about debouncing. I first mentioned debouncing in episode 2 of the tutorial series when we first hooked the button up to the Arduino to control something in the software. We ran into this issue where when you push a button, instead of just going from low to high, it actually jumps up and down first a little bit before it settles on a value of 5 volts. This is going to be a huge problem in interrupts because 1, we can't use the delay function inside interrupts, and delay was our primary means in software of dealing with this. We would just read it and then delay until after this had passed and then read it again to get the actual value. But if we can't use delay functions in interrupts, how are we going to deal with this? If we use this straight up in an interrupt function, we're going to have a problem because there's several rising edges that occur here, and we only want one rising edge. So what will happen is we'll actually execute the interrupt function several times instead of just one, which is going to cause errors in our program. The reason you can't use the delay function in interrupts is because it depends on the same timer that's used to handle the interrupt on the Arduino. Let's talk about how we can fix this. The answer is a hardware solution so that we don't have to use any functions in the Arduino software. Here's what our circuit looked like the first time we hooked the button up to the Arduino. We had a 10K pull-down resistor to ground, a connection from that resistor to the pin, and a button that connected from there to 5 volts. When the button was undepressed, the pin was pulled down to ground through the 10K resistor. When the button was pressed, it was pulled up to 5 volts through the button. Now, let's figure out how we can use a similar setup, but do it with a debounced signal coming out. This is the setup we'll use to accomplish a debouncing in hardware before it ever gets into the software of the Arduino. First off, we're going to change our pull-down resistor to a pull-up resistor. I'll explain why that is in a minute. We're still going to use a 10K resistor, but we're going to add a capacitor across the button. I'll also explain that in just a moment. This is an inverting Schmitt trigger. The inverting Schmitt trigger will smooth out the signal that we're going to create from this RC circuit or resistor capacitor circuit and then invert it back. The reason we use the pull-up resistor is because we're using an inverting Schmitt trigger, which changes the signal from high to low and from low to high. Therefore, we wanted to change the default state from a low default state here to a high default state here, and then this will switch it back to what we want. After we implement this, the signal going in will look like this, exactly what we want for an interrupt. Awesome. But now let's see why that's happening. The reason behind this circuit's ability to debounce our signal in hardware is called an RC circuit. RC stands for resistor capacitor, and it just means that we have a resistor and a capacitor in series. So let's take a simple example here. If we have 5 volts going through a 10K resistor and a 10 microfarad capacitor, exactly as set up in the schematic I just showed you, we can find a time constant called tau. Time constant equals the resistance times the capacitance value. The time constant is the amount of time it takes for the signal to decay from 5 volts down to ground. There's a decay time because capacitors store charge. That means it's going to take a little while for it to go to 5 volts down to ground because this holds charge in it. If we do this calculation out, we'll see that the decay time is 0.1 seconds, more than enough time to allow the button to debounce, but less than ordinary human reaction time. So, if we now look at this graph here, which shows voltage versus time, this explains the RC constant that I was talking about. If I push the button down right here, it's going to take some time for it to decay from 5 volts down to ground. You'll see that the capacitor helps smooth the bouncing that we saw before, but makes it no longer linear. It no longer just drops straight down. Now it decays down to ground. When we release the button right here, it'll slowly curve back up from ground to 5 volts. This is also determined by the RC time constant. Now, let's add our inverting Schmitt trigger. The inverting Schmitt trigger does two things. The first thing is it flips all logic levels. 1 becomes 0 and 0 becomes 1. But the more important thing is that it's going to smooth out this curve. It has very certain voltage points after which it sets the signal to a default value. So at a certain point, when it hits a certain voltage decaying here, the Schmitt trigger is going to set it high, which is what happens right here. And then the same thing going back up. Once it hits a certain voltage value, it'll get set low. So the Schmitt trigger turns this inverted into a square wave. And that gives us exactly what we want to go into the interrupt on the Arduino. Awesome. Here's what the circuit looks like wired up. We're using the same push button as before. Here's our 10 microfarad capacitor and our 10 kilo ohm resistor. This is our inverting Schmitt trigger IC. It actually comes with 6 inverting Schmitt triggers in it. We're just using one of them. It gets power on the top rightmost pin and is connected to ground on the bottom leftmost pin. This is a very common configuration for 74 series integrated circuits, of which this is one. Here's the code that we're going to be running on this circuit to see if our hardware debouncing works. Does it look familiar? It should. It's the exact same code that we ran in tutorial 2 before we added software debouncing. When we ran this in tutorial 2, we ran into all kinds of issues with the LED not turning on when it should and not turning off when it should. Now we're using that exact same code that was prone to error in tutorial 2, and it should work thanks to our hardware debouncing in tutorial 10. So let's load it onto the Arduino and see how well it works. Okay, now that the software is downloaded onto the Arduino, keep an eye on this LED which is connected to pin 13, and we'll control it with this button as we set up in the program. On, off, on, off. Works perfectly, and we didn't have to do any software debouncing. Remember what a pain that was last time? And all we had to do was add 2 components to the circuit. Awesome. Now that we know how to debounce a button correctly in hardware, we can use it as an interrupt into the circuit without having to worry about any bouncing issues. So let's use a switch input into the circuit to do something interesting and make a kind of mood color LED chooser that you control with your hands. Here's what we'll need to accomplish this. First off, we'll have 3 different colored LEDs. You can choose whatever color you want. I chose yellow, red, and green. These should be connected to 3 PWM enabled pins in the Arduino so we can change their brightness. Each one will have a current limiting resistor of 150 ohms as we usually do. Next up, I'm going to attach an infrared distance sensor. This is one that we've used in several tutorials before. It's a sharp infrared distance sensor. It has voltage connection, a ground connection, and an outputs and analog value, which will attach to analog input 0 on the Arduino. Lastly, we have our debounce button input. So just like I showed you before, we have our 10K resistor, our 10 microfarad capacitor. If you're using an electrolytic capacitor, make sure the negative end goes to ground because those are polarized. And we have our switch here and our inverting Schmitt trigger here, which then feeds into pin 2. I've chosen pin 2 because pin 2 is one of the 2 interrupt enabled pins on the Arduino. It's interrupt 0, so when we refer to it in the program, we'll actually be referring to 0, not 2. Okay, great. And what this switch will do is when we push a button, it will change between the LEDs, and the distance sensor will allow us to change the brightness of each LED. So you can place your hand above the distance sensor to change the brightness of the LED that's currently selected. Get it to a brightness you like, push the button, and it'll go to the next LED, and then you can set the brightness for that LED. And so you'll be able to set the brightness for all 3 LEDs and then leave them set at that value just by moving your hand up and down over the circuit. It should be pretty cool. So let's write the code for it. I've already set up a framework for our code. Let's start by going through all the comments that I made and filling in the appropriate information. The first thing we have to do is choose which interrupt we're connected to. So instead of saying we're connected to pin 2, we're going to say we're connected to interrupt 0, because that's really what we care about. So we'll say the button interrupt instead of the button pin is equal to 0, which is pin 2 on the Arduino. And we'll just comment that so we know. Next, we need to configure all the pins that the LEDs are connected to. Int yellow LED is connected to 11. Int red LED is connected to 10. Int green LED is connected to 9. Now I'm going to do something interesting here, which is to create a fake LED that I'm going to call null LED. The reason I'm doing this is so that we can lock the LEDs to a certain brightness level. Because we'll be scrolling through each of the LEDs to set their brightness, we want to choose the opportunity to scroll to something that doesn't exist so that these stay where they are without currently always fluctuating with the infrared sensor. You'll see what I mean in a minute when I implement this. And then the last thing is to set up the pin for the distance sensor. Int dist pin equals 0. It's analog input 0. Okay, now let's set the pin modes. We need to set these all as outputs. Pin mode red LED is an output. Pin mode green LED is also an output. Yellow LED, also an output. And we don't really need to set this, but I'll just do it anyway. Pin mode null LED, an output. I just chose 6 because it was another PWM pin, but it doesn't really even have to be a PWM pin, to be honest. Okay. And now let's attach our interrupt. So to do that, we use a command called attach interrupt. And we feed it 3 things. What interrupt we're connected to, which we defined earlier as button int, so interrupt 0. A function that we want to run when the interrupt is detected. And when we want to run the interrupt. So remember I talked about this earlier in this episode. Rising, we want to detect when the button goes from low to high, which should be perfect based on the setup of our button. We're connecting to interrupt 0, which is set by button int. And we're going to run this function called swap whenever that button is detected. And we'll write swap in just a moment. Okay, before we write swap, let's write the loop here. So the loop is just going to be doing what we want the program to do. Whatever LED it happens to have selected at the moment, we'll have it change the brightness based on the infrared distance value. So we've done this before. We'll do int dist equals analog read the distance pin. We'll change that to a brightness by mapping it. Distance 0. 1023, 0, 255. Okay, good. And then we'll just have it write that to the LED. But, gee, how do we know which LED we're currently on? Well, okay, let's put it in and then we'll make a variable to control it. Analog write, we'll call it selected LED. And brightness. So now you can see exactly what we need to do here. We need to use this swap function to change what selected LED is. So let's define selected LED up at the top here. There's one very important thing though, which is that you need to define anything that gets modified by an interrupt function as a volatile. So we put volatile int selected LED equals, let's start it off on the green LED to begin. So what volatile means is that this integer can potentially change in the middle of execution here. If you don't define it as volatile, you're going to run into all kinds of weird things happening. Okay, perfect. So that should do what we want, and we'll start it off as green LED. Now all we have to do is write swap. So what swap should do is every time the button is pressed, it should increment through the LEDs and change selected LED from green to red, and then red to yellow, and then yellow to null, so that it locks the LEDs on whatever brightness setting we have them, and then from null back to green so that we can do it again. So that's just going to be a couple if statements. That's pretty straightforward, right? So if selected LED is currently set to green LED, remember we'd use our double equal sign in if statements, then we'll change it to red LED. Oops. And if selected, or we can do else if actually to save us some processing time, else if selected LED equals red LED, we'll change it to yellow. Else if again, oops, I have a spelling error up here, huh? Else if selected LED. Oh, I also forgot my double equal sign. Hopefully you guys caught that, right? And I have a capital S. I'm making errors all over the place here. Selected LED equals yellow LED. Then we want to change it to null. And last but not least, otherwise, we'll change it back to green. All right, let's just check that over for mistakes. That looks good. Good, 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 good. Okay, that looks good. And remember, you don't actually need brackets if you only have one line of code after an if statement or a while loop or a for loop. You don't need brackets always. Okay, so this code looks done now. Let's run it on the Arduino and see how our neat little visualizer works. We have the code on here now, so let's see how it works. Let's choose a brightness for green first. We can see the brightness changes with distance. Pick something right there. Okay, now it moves to red. We'll make red a little bit dimmer, I think. How about there? And now we can set yellow. Let's make yellow nice and bright. Okay, cool. And then we press it again, and it goes to that null LED, and they're all set at those levels. And then we can, of course, go through and change them again if we want. Awesome. Thanks for watching my 10th Arduino tutorial. I hope you guys enjoyed learning about interrupts. They're really, really useful. And maybe you guys got some good ideas from the project we did today. I think you can make a really cool musical theremin out of it. Maybe you guys want to experiment with that. I'd love to see any suggestions that you guys have or projects you could work on using that code that I showed you. This is going to be the last consecutive Arduino video that I'm making, as I mentioned at the beginning. I hope to make more of them in the future, but I can't continue making them every week during the semester. It's too crazy. Hopefully I'll be able to do some written tutorials though, and I'll be able to answer your guys' questions if you have any questions. Always remember you can post them on YouTube, on my blog, or on element14.com, and I will check them out. So thanks again for watching. I really appreciate anyone who watched through the whole series and all the people who gave me feedback. It was really spectacular, and I really enjoyed making these because of all the great feedback I got from you guys. So thanks again, and I'll see you soon. Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at element14.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.